Here in section 8.4, we're going to take an idea from Algebra 1, systems of equations, and we're going to expand it into more equations and more variables. Back in Algebra 1, you studied 2 equations with 2 variables, and today we're going to look at 3 equations with 3 variables, but really, once you see how 3 equations and 3 variables works, you'll probably be able to imagine how to expand beyond that. 4 equations and 4 variables will work in a similar way, 5 equations with 5 variables, and so on. The more equations and the more variables you have, the more time-consuming the problem is. But the basic technique will be the same as what we're going to be going over today. So, first, basic issues for these new sorts of things that we're going to be looking at. If you have 3 variables, x, y, and z, if you want to think about the graphs can't just have an x and a y axis. They have to have an x, a y, and a z axis. So that means your graphs are going to be 3-dimensional graphs. The other thing is, and this one isn't as obvious, the graphs you get for things like this, the graphs of something like this is not a line. This is a plane, a flat surface. Now, it's probably a flat surface at some sort of an angle with a slope. It's probably not horizontal or vertical, but it is flat. It's not going to be curved at all. But if you have 3 of these things, x, y, z, here's one plane, x minus 2y minus z equals 1, here's another plane, here's a third plane, the answers that you're going to be expecting to get from something like this, they're going to be points. Just like we had back with 2 equations with 2 variables. The only difference is you're going to have an x-coordinate, a y-coordinate, and a z-coordinate. So you're expecting for an answer to a problem like this to be some number, comma, some number, comma, some number. With, of course, 2 exceptions that you're probably already thinking about. Back when you talked about 2 equations with 2 variables, there were 2 exceptional type answers that you could get that wouldn't fit this pattern. The same thing is true here. The other 2 sorts of answers that you can get are, of course, possibly no solution. It's entirely possible to build an equation or a system of equations that has no solution at all. Or the other possibility is infinitely many solutions, just like we had before. You can have more than one solution, but if you do, it's going to be an infinite collection of solutions. Now, those 3 cases are still going to apply here, but to see how they apply, we're going to have to take a look at pictures. Please be aware, before I scroll down any further, you will never be expected to draw these pictures yourself. They're 3-dimensional pictures. Trying to draw them is a significant artistic challenge. How do you represent a 3-dimensional graph on 2-dimensional paper? You know, it's not worth it for us to ask you to draw 3-dimensional graphs. Plus, the 3-dimensional graphs are almost impossible to read, to tell where the intersection is. So it's a completely useless technique for answering things except for this one tool, which is to show you what kinds of things are possible. And when you have 3 flat surfaces intersecting, there are a lot more things that can happen. There are a lot of different ways you can have 3 surfaces all intersecting each other. Typically, you're going to have something like this, where there is one single point in the intersection of all 3 surfaces. That point is on all 3 surfaces there. That is the point of solution. But these other sorts of arrangements are possible as well. And if you take a look at them, there are 3 different pictures there that have no solution. This is certainly no solution. There is no point of intersection at all between any of the surfaces, so no solution. This is also no solution, and so is this. Even though in those 2 pictures, some of the surfaces intersect each other, there is no point that's on all 3 of them at the same time. So there is no overall solution that solves all 3 equations. So all of those there are no solution. But then this one here is a different thing. There are points that are on all 3 surfaces. There's a point over here that's on all 3 surfaces. There's a point there, and there, and there, and this way and then that way. That's what infinitely many solutions looks like. Well, unfortunately, that's not the only way you can get infinitely many solutions. That's one way that you can get infinitely many solutions. But of course, it's possible that when you draw the three graphs that go with the three equations, it's possible that all three graphs are duplicates of each other. We saw that with lines, where you could have two equations that look different but actually graph the same. The same thing can happen here. You can have three planes that the equations look different, but the graphs come out the same. And that's, of course, also infinitely many solutions. And then there's a case that's kind of a mix of no solution and infinitely many solutions. There's a case where you have two planes that are duplicates, and then a third plane that's parallel to them. So two of the planes are exact copies of each other, and if you just look at those two equations, you might recognize that those equations actually give you the same picture, and that might make you think that there's infinitely many solutions, but then the third equation gives you a plane that's parallel, so you actually end up with no solution at all. So this is also a no solution situation. Notice that the kinds of arrangements that are possible with three planes, there are way more possibilities here than back when we were talking about lines. With lines, there were only three things. There were parallel lines, duplicate lines, or normally intersecting lines. Here, we've got, 1, 2, 3, 4, 5, 6, 7 different arrangements that are possible, some of which are no solutions, some of which are infinitely many solutions. Like I said, though, these graphs are meant to point out to you that there are a bunch of different complexities in how they might be arranged, but you don't actually have to draw these graphs or use these graphs yourself. What you're going to want to do, of course, is solve the system of equations. And we have two techniques, substitution technique and the elimination technique, just like we had with two equations and two unknowns. It's going to take a little bit more work to apply them. It doesn't work quite so instantaneously, but it can still work in a very similar fashion. So, let me walk you through solving this one with substitution. Just like with two equations, you pick an equation, solve for a variable. So I'm going to take this top equation, I'm going to solve it for z. So we're going to get z equals, well, I'll move the x over, and I'll move the y over, so I'll have z equals negative x minus y. And then I'll plug in for z in the other equation. Oh wait, there's two other equations. Well, I'm going to plug into both of the other equations. I'm going to take each of those other two equations, and where there used to be a z, I'm going to plug in the thing that z is equal to. Z, we figured out, was equal to negative x minus y. So this substitution technique is a little trickier than it is with two equations. You're plugging into two alternative equations rather than one, so that's a little bit more work. But ultimately, it's the same basic idea. And then, just like you would expect, you're going to distribute and collect like terms, and you're going to distribute and collect like terms. When you distribute and collect like terms here, something really nice happens in that top equation. If you haven't seen it yet, you might want to pause the video and work it out yourself, and you'll see. Yeah, that top equation actually simplifies down to y equals negative 1. And the second equation, when you're all done simplifying it, it's x plus 6y equals negative 3. So this turns out to be a kind of easy finish to the problem that you wouldn't normally expect. They aren't normally as nice as this, telling you what y is right off the bat. But hey, if we're lucky enough to get that, let's use it. I will, of course, plug in for y in the other equation. So, negative 1 goes there. 6 times negative 1 is negative 6. Move the 6 to the other side. You get x equals 3. And at this point, we have y, we have x, and we almost have z. We just have to take the x and the y we just figured out and plug in for z here. Negative x minus y. We figured out that x came out to be 3. Y came out to be negative 1. Watch out for the double negative right in there. I mean, that's a rookie mistake that any of us could make pretty easily. And we end up with negative 2 for z. Please don't forget that with these problems, your answers have to be in point notation. So I would expect your answer to look like this. 3, negative 1, negative 2. Parentheses around it, comma between the coordinates of the answer. Make sure you write your answer in point notation. So, substitution works with 3 variables and 3 equations. And if you're looking at this, I bet you can imagine how it would work if you had 4 equations with 4 variables. You'd pick one of the equations, you'd solve for one of the variables, you would plug into the other equations to reduce down to one less variable. And then you would do it again. Take one of those equations, solve for one of the variables, plug into the other ones, and get one less equation. And that's really sort of the overall big picture here. You could have 20 equations with 20 variables, and you would just substitute to eliminate one variable in one equation down to 19 and 19, and then 18 and 18. And it would take a really long time, yeah, but the procedure should be pretty clear. Let's also look at using the elimination method, because you know there are plenty of situations where substitution will be kind of iffy, and elimination might be a bit of an improvement. One of the suggestions I'll give you is, since you're going to be doing a bunch of multiplying equations and adding them together, it would be a good idea to label the equations with letters or numbers, like equation A, B, C, or equations 1, 2, and 3, just so it's easier to keep track of which one is which. So, what we have to do here is eliminate a variable and produce 2 equations with 2 variables, kind of like what we did with substitution. So we look through these equations here and we try to imagine which variable looks easiest to cancel out in a pair of equations. And I'm looking at these and I'm actually thinking that the letter y appears to be the easiest one to cancel out. In particular, I'm looking here and saying, wow, that's going to be super easy to cancel out y. I'll take equation 2 and equation 3, and all I have to do is pick one of the equations and multiply by minus 1. So I'll take the second equation and I'll multiply by negative 1. So it'll be negative x minus y minus 2z equals negative 5. And add that to the equation 2. And the y's will cancel out. We'll get 4x, no y's at all, minus 3z equals 2. Now the problem is that equation still has x and z in it. I can't solve that for just a single variable. So what I need now is I need another xz equation. I'm trying to produce 2 equations with 2 variables here. So now I have to pick another pair of equations, not equations 2 and 3, 1 and 2 or 1 and 3 instead, and also eliminate y. So let's say I use equations 1 and 2, and if I want to eliminate y, I'm going to have to, well, let's see, what seems easiest? I'll take equation 2 times negative 2, and just leave equation 1 alone. So 2x, 2y, minus 4z equals 6 versus negative 10x minus 2y plus 2z, watch out for the double negative, equals negative 14. And you get negative 8x cancels, minus 2z equals negative 8. And then, to continue from here, I think you know what you're going to be doing. You're going to be solving 2 equations and 2 unknowns, and you already know how to do that from Algebra 1. And I'll give you one little hint just to make sure you know that you've done the problem right at the end. The answers come out to be fractions, so checking them is going to be a bit of a pain.